Explain the following terms. First, forced vibration with rotating unbalance. Second, forced vibration with reciprocating unbalance.
Due to rotating and reciprocating unbalanced masses in the machine, periodic disturbing force exists and which results in vibration. Let us first understand the forced vibration with rotating unbalanced. If we observe, here is the machine of mass m which includes the rotating unbalanced mass m0. Now this mass m0 is placed at a distance e from the center O. This machine is connected to the spring with stiffness k and damper with damping coefficient c. Now whenever the vibration occurs due to this unbalanced mass m0, the machine vibrates in upward and downward direction from its mean position. Now we will consider when the machine moves in upward direction through a distance x. So displacement from its mean position we will consider here in upward direction with distance x. Then this center O will be at this new position with center O1. Now at this point we will consider this mass m0 will remain at its position only. That means for this diagram angle theta is equal to 0 for this mass m0 which is rotating unbalanced mass. But we know that this mass m0 is rotating about the center O. So when it rotates about the center O, this is the new position of the mass m0. Now we have to find out the displacement of this mass m0. So how to find out? So we will consider this angular displacement of this mass m0 is to an angle omega t. So for this case, for mass m0, theta is equal to 0, and for this case for mass m0 angle theta is equal to omega t. Now how to find out the displacement of this mass m0? So initially m0 is at point A, and when it rotates about the center O, then here is the new position A dash. So I will take here, or I will draw here one perpendicular line on the axis of the machine, that is axis of this center. So here is the center O. Now we have to find out this distance A dash to B. So how to find out? So if we observe, here is the triangle OBA dash. Now in this triangle, how to find out this distance A dash to B? So here angle is known omega t, and here we have drawn the perpendicular line. So this is the right angle triangle. So we can say that this A dash B is equal to E sin omega t. So I will write here E sin omega t. Now how to find out the displacement of the masses? So here this capital M is the total mass of the machine including m0. So we have to first take this displacement x is for mass m minus m0, that is known as net mass. So the displacement for the net mass m minus m0 is equal to x. And what is the displacement of this mass m0? So I have shown here in this diagram. So with the displacement of this mass m0, that is we have to find out the total displacement. So here the initially mass is at this position along this horizontal line, and finally this mass m0 is at point A dash. So how to find out this? So here this displacement is x plus this vertical distance is sin omega t. So the displacement of this mass m0 is x plus e sin omega t. So we have to prepare one table. So here net mass m minus m0, displacement is x. But the mass is rotating about the center. So what is the rotating unbalanced mass m0 displacement? So it is x plus e sin omega t. So we have to write. Now we will find out the velocity. So velocity, that means we have to differentiate with respect to time t. So x is having x dot, and what about x plus e sin omega t? So here is sin omega t is the term which includes time. So we have to differentiate this as a cos omega t into omega. So how we will write here? X dot plus e omega cos of omega t. Now we will find out acceleration. So for this net mass, acceleration is x double dot, and for rotating unbalanced m0, acceleration is x double dot plus, now this cos omega t is having differentiation minus sin omega t into omega. So here omega multiplied by omega is omega square. So we will write here minus e omega square sin of omega t. So this is the acceleration for both the masses. Now we will draw the free body diagram. Now we know that when the vibration occurs, we have considered here the machine is displaced from its mean position in upward direction. So we will show here the displacement of the machine x is in the upward direction. So all the forces, that is the inertia forces, will act in the opposite direction. Now the inertia force, that is the resistance force, is applied due to this net mass m minus m0, and also due to this rotating unbalanced mass m0. So how to show these inertia forces due to mass? So we will first take the net mass. So for net mass, we will show here the inertia force in the opposite direction, that is in the downward direction. Now mass multiplied by acceleration, that is m minus m0 multiplied by acceleration. So this is the inertia force due to net mass. Now we will show the inertia force due to rotating unbalanced mass. So I will show here, that is it is also in the downward direction. So here mass, rotating unbalanced mass, is m0 multiplied by acceleration. So acceleration is here. So we have to write this. So I will write here as a m0 in bracket x double dot minus e omega square sin of omega t. So these two are the inertia force. Now inertia force due to mass. Now we have to write the external forces. So external forces are here because of spring with stiffness K and damper with damping coefficient C. So we will show here. So these external forces are also in the opposite direction of this X. So we will show here. So the spring force will be Kx and this damper force will be Cx dot. With reference to this free body diagram, we will find out the amplitude of vibration. Now we will apply here the principle of inertia force plus summation of external forces is equal to 0. Now if we observe inertia force and the external forces all are in downward direction. So we will use here the same sign, that is positive sign. We can also use here negative sign, but we will use here positive sign. So we will write here m minus m0 x double dot plus m0 in bracket x double dot minus e omega square sin omega t plus cx dot plus kx is equal to 0. Now we will simplify this. So how to simplify this? We will multiply with this bracket. So mx double dot minus m0 x double dot plus m0 x double dot minus m0 e omega square sin of omega t plus cx dot plus kx is equal to 0. Now if we observe here minus m0 x double dot and plus m0 x double dot is getting cancelled. So we will rewrite the remaining formula. So here sin omega t term we will shift to the right hand side. It is also having minus sign. So when we transfer to the right hand side, it will become plus. So we will write here capital M x double dot plus cx dot plus kx is equal to m0 e omega square sin of omega t. So this is the equation for this system, that is with system with rotating unbalanced mass m0. Now we will compare this equation with the equation of forced vibration, or we can say forced damped vibration. So we know that the governing equation is mx double dot plus cx dot plus kx is equal to Fo sin omega t. Now if we compare these two equations, so I will write here this is the equation 1 and this is the equation 2. Then instead of small m, here is the capital M. So capital M is nothing but this mass of the machine including unbalanced mass m0, and instead of this Fo, here is m0 e omega square. So we can write here as a Fo is equal to m0 e omega square. We know the formula for the amplitude of forced damped vibration. Capital X is equal to Fo by K into magnification factor, that is Ohm. So this is the formula for equation number 2. So we will write here, or we will make bracket, this is the formula for the equation number 2. Now we have to replace the terms. So instead of Fo, we will use here m0 e omega square, and this K, that is the spring stiffness K, is having formula in terms of m. So if we compare these two equations, then instead of small m, we have to use here capital M. So we will write that formula, omega n is equal to under root of K by M. We will make square on both sides. Omega n square is equal to K by M, and K is equal to omega n square capital M. Now instead of K, we will write this because we have replaced this small m instead of capital M. So I will write here Fo, that is capital X is equal to, instead of Fo, m0 e omega square, instead of K, omega n square capital M. Now we know that the ratio of omega by omega n is known as frequency ratio, that is R. So omega square by omega n square, that is R square. So how we will write here? So capital X is equal to m0 e R square by capital M multiplied by magnification factor, that is Ohm. So this is the final formula. So here we have to multiply with this magnification factor Ohm. So this is the final formula to find out the amplitude for the system with rotating unbalance. Now we will move to the next point, forced vibration with reciprocating unbalanced. Now if we observe the diagram, here is the piston cylinder arrangement, and the piston is connected to the crank with the connecting rod having length L. Now the unbalanced reciprocating masses is m0. Now if we observe here, this crank is rotated about the center O, and it is rotated through an angle omega t. Here capital M is the total mass of the machine including this reciprocating unbalanced mass m0. Now this system is connected with the spring with stiffness K and damper with damping coefficient C. Now we will concentrate on this rotating and reciprocating motion. So I will redraw here the diagram. So if we observe, we will consider this vertical axis as a horizontal axis. Then here is the mass, reciprocating mass with unbalanced mass m0. This is the connecting rod of length L, and this is the crank radius R. Now I will take here this angle from this vertical axis to the crank is theta. So I will write here the angle as a theta. Now we know the formula for the inertia force for this system, that is the crank and piston arrangement. So what is the formula here? So Fi, that is the inertia force, is equal to m0 r omega square in bracket cos of theta plus cos of 2 theta by n, where n is the obligatory ratio and it is equal to L by R. So this formula is applied to this diagram. Now we will convert this cos theta. So we know that this cos theta is equal to sine of 90 minus theta. So instead of cos theta, we can use this sine of 90 minus theta. So both the meaning are same. Now if we observe this diagram, then what is this sine of 90 minus theta? So if we observe the angle in between this vertical axis and horizontal axis is 90, and 90 minus theta is equal to omega t. So we can also write sine of 90 minus theta is equal to sine of omega t. Now instead of cos theta, we will replace here with sine of omega t. So how we can write here? So this is the formula for this system. Now if we compare with this system, then instead of r, that is the crank radius r, we have to take as a e. So we will take here m0 e omega square. Now cos of theta we will write as a sine of omega t plus cos of 2 theta, that means sine of 2 omega t divided by n. Now n is the obliquity ratio. Now for high speed engine, this n is large. That is, when the value of n is very large, then what will happen? Because it is in the denominator, this term will become negligible. So for the high speed engine, we have to neglect this second term, sine of 2 omega t by n. So what is the remaining formula? So inertia force is equal to m0 e omega square sine of omega t. Now if we compare this with Fo sine omega t for the force damped vibration, then Fo is equal to m0 e omega square. So the value is same as for the previous case for rotating unbalanced. So we have to use the same formula to calculate amplitude of vibration for the reciprocating unbalance as with that we have find out with the rotating unbalance.